notes coming round. They're not precisely what's up on the board. There's more in there than that goes up here. Example, problems solved, and so on. So, session outline. By the end of this session, you should understand and be able to calculate current and voltage in series circuits, current and voltage in parallel circuits, current and voltage in combination circuits. Okay. So, there are a number of conventions for representing the different voltages you might find in a circuit. One way of representing a DC source is to put the circle with a solid line on top and a dashed line underneath to represent a DC, direct current voltage. And you have an arrow that indicates and points towards the positive end of that DC voltage, and you usually represent a source by the letter E for electromotive force, i.e. a source of electrical energy. So the arrow points in the direction that current will flow away, conventional current will flow away from that. So for a source, the voltage arrow points in the direction of current flow. Yep. And I say conventional because actually the electrons are flowing in the opposite direction. But I always teach conventional current flow and not electron flow. It causes lots of confusion. All right? So we'd say that that end of that source is the positive end, and that end's the negative end in this case. Okay? If we show a resistor with a current flowing through it, R1 with current I flowing through that, we'd put an arrow above it. Please do not put arrowheads on both ends, because the arrowhead indicates the polarity of that voltage across. This is the most positive end, that's the most negative end. And the arrow points opposite to the direction of current flow through the resistor. Yep. And it's really important that you get this, because when we go on to do Kirchhoff's laws next week, labeling up your diagrams with the arrows in the right direction is the key to getting the right answer to some of the problems. Any volt drop, the voltage arrow opposes the current arrow that's going through that device. So we got current going that way, voltage arrow points that way. If the current was going in the opposite direction, the voltage arrow would be in the opposite direction. Alright, everybody happy with that? So we've got some notational ideas that are important to follow. So, if we look at the series circuit first, remember last week we talked about resistors being connected end on end, or resistors in series. Here we've got a series circuit of two resistors. When we have that, in a series circuit, we only have one current flowing through all the components. If we put an ammeter in there, and measured that current 5 amps, we could equally put an ammeter here, we'd measure 5 amps, and an ammeter there, we'd also measure 5 amps. There's only one current around that one loop. So in an all-series circuit, all the components have the same current flowing through them because there isn't any leaks. Every electron that leaves one terminal has to end up back at the source. Yes, in total, we're going to do parallel after this, but in total, every amp that leaves the source ends up back at the end. It's the only thing that we have come into our house, go through our house and leave, and we still pay for it. Yeah, electrons. It's one of the only things. Yeah, I guess so. Yeah, it goes through it. Yeah. Yeah. Well, hopefully the electricity doesn't end up going through your body. Right. So that's what happens. However, these individual resistors will be of individual values. We can calculate these voltages. The total current here, I, will be calculated from the applied voltage divided by RT. Okay. Each individual voltage is related to that current, but the resistor value. So, what will happen is, we'll get a portion of that voltage, if that's 10 volts, and as you'll see in a little while with an example, if these two were 10 ohms, that voltage would divide equally between those two resistors. We'd get 5 volts and 5 volts. The point being made is that a series circuit is a voltage divider. So if we add a third resistor in there of the same value, we'll divide it up 3 times. And we'll formalise that next week with Kirchhoff's voltage law that you may remember from earlier electrical principles module on BTEC if you've done that. Okay? But the important thing about, if it's all series, you divide the voltage up. Classic example of a circuit like that is Christmas tree lights, all connected in series. The lamps are 12 volts, but you've got 20 of them all connected in series, so they each get 12 volts at the 240. But you take one lamp out, because it's connected in series, take one lamp out, they all go off. All modern ones, I'm not so sure are like that, but that's how they used to be years ago. Alright? So, example problem. Resistors of value 20 ohms. Pull that down a bit. $75 ohms and 120 ohms connected in series across the supply DC of 100 volts. Calculate the current flow in I. So let's put an arrow on there. I, put a voltage arrow on our source, pointing with the flow of current. And we know that we'll get volt drops here, V1, V2, and V3. And all my arrows point on those against the flow of current. Yeah? Calculate the current flowing and the volt drop across each resistor. So how are we going to start that problem? V equals IR. Yeah, go on. Or find the current and then I is equal to V over R. Yes, so first of all, calculate total resistance. RT, R1, plus R2, plus R3. Plus 20, plus 75, plus 120 equals 215. How many? 215. 75 and 120 is 195. 20 is 215. Oh. First part of the problem solved. Yeah. Now we can go I is equal to E over RT. 100 over 215 equals 0.47 amps equals 470 milliamps would be another way of writing it. Now how do we find V1? Yep. I times, you need to specify which R. R1. If we want the volt drop across R1, we isolate and just use the resistance for R1. Yeah. So that's R 0.47 times the value of R1 is 20 equals 9.4 volts. V2 I R2 0.47 times 75 equals 35.3, let's say, one decimal place. All right, and V3 is I times R3 equals 'Yeah, and if you add all those up, what do you get? And it's only not exactly equal to 100 volts because we've rounded. Yeah. All the voltage is shared between all three resistors in a ratio of those resistors. So what you'll notice that the bigger the resistor, the bigger the volt drop across it. Okay. If you think in terms of a pressure system, if we got a head tank, that's our positive pressure, and then that comes down, falls in a pipe, and then we reduce the diameter of that pipe, we get a higher pressure above than we do below. That's what's happened. Every time you put a resistance in a circuit, you're reducing. The voltage is the pressure that forces the current through. So when current flows through a component, through a resistance, we always get a potential difference of volt drop across that component. And then when you go around one series circuit, we drop the voltage in proportion to the ratios of the resistors. Bigger resistor gets the bigger volt drop. Alright? Current is the same. What have we got on my next slide? Yeah, okay. So, there is a formula for the 2 resistor voltage divider. That means that you can do the calculation for V1 and V2 in one go. And in some calculations later on, in electrical principles, you may need to do that all in one go. Alright? So, we go through that. This is keeping it to algebra, but it's similar to the problem we just looked at. We calculated RT by adding the resistors together. So the total resistance of this circuit is R1 plus R2. If we then substitute that into Ohm's law for I, we get I is equal to E over R1 plus R2. So we can directly get the current calculating in one go. We also know that V1, the volt drop across the resistor R1, can be found from I times R1. So if we substitute that equation into that for I, that's what we end up with. Okay, so what we've done is we've substituted in this equation V1 is equal to, but instead of writing I, we've written E over R1 plus R2. That's the current, and then we've got to multiply that by R1. So now we've got one big formula, that one, to find the voltage V1 if we know the supply voltage and the value of the 2 resistors. Equally, we find V2 by multiplying E by R2 on the top and dividing by the 2 resistors added together. Voltage divider rule. Okay? Well, can remember that. You can remember that you can do Ohm's law and do each calculation separately like we did in the first part. Sometimes there's instances where you're better off or need to do it this way, but not that often. Okay? So if you look through electrical principles books, you're going to find that they talk about the voltage divider rule, and it's a quick way where there's only 2 resistors to get the value of volt drop across one of them. I think that'd be a bit more messy when you start a substitute in. Yeah, you're better off just to use that for the 2 resistor voltage divider. All right. Example problem: a voltage divider is to give an output voltage of V2. So let's call this V2, and we want 18 volts. From a input voltage of E is equal to 45 volts. Given that R2 is 50 ohms, calculate the required resistance for R1. So this is the question mark. And you've got no current. Yeah? Not been given a current. Don't know that resistor value, so you can't calculate the current. Or can you? We'll come back to that, but you can. Well, you tell us now, Lewis. You know that's one current, so you've got 18 volts there and 50 ohms, so you could calculate the current using those two values. Okay, so we'll look at that in a minute. First of all, by voltage divider rule, we know, right, that do you want to do that? What do you say? $45 volts.
No, 45 over 18.
Where did you get that from, Dom? $18 times 50. Yeah. Let's just do the voltage divider rule first, right? By voltage divider rule, yeah, V2 is equal to E times R2 over R1 plus R2. All agree with that? Yep. Now how can I rearrange that so that I get R1 on its own? Remember, what you want to remember is that fraction, listen, just a minute before you go on, that fraction implies that those two are together in brackets. Yeah, good. So hang on, let me do that, Lewis. All happy with that? Now what can you do? Yeah, so we can do R1 plus R2. The brackets can go now. Now it's not a common factor. Is equal to E R2 over V2. And then, last of all, R1 is equal to E R2 over V2 minus R1, R2. Alright, now we can put our numbers in. E was 45, R2 50, V2 was the 18, and R2 was 50. Equals. .45 by 50 is 225. That's 75 altogether. Everyone else agree with that? Yeah? You, Dom, yeah? Right, going back up the top, so we can do that in one go by voltage divider rule, okay? Or we could do the alternative method is to say I is equal to V2 over R2. That's 18 over 50 equals what? You done that, Lewis? Didn't you?
Yeah, that's
0.36 amps. Yep. Now where do we go? Yeah. VR1 is equal to E minus V2. Yeah. Remember we added them up. They equaled, so we rearranged that. We added V1, V2 and V3 in that other. They totaled up to E. So that's that just rearranged. That's Kirchhoff's law, but I haven't taught you it properly yet. Yeah? So that is equal to 45 minus the 18, which is 27 volts. And now we know that we've got 27 volts across there, so we can use Ohm's law with the current we calculated in the first part. We can say R1 is equal to 27 over 0.36 equals, and the answer is three significant figures. 75. So it's not 75 point some odd. No, that was an exact current. Was I didn't know whether it was or not. No, that's not rounded at all. That one. Okay. So the only compelling reason to go through all of that is if you don't want any error, because there's a potential for error in this bit as you round the individual calculations. All right. You could be asked to, yeah. Okay. I mean, like last week, we done the combination circuit with one resistor. This combination circuit, R1 followed by 2 in parallel. There's a bit in electrical principles, year 3, where you'd need to be able to have the total resistance of that written out in one go using. So you'd have to do RT here is equal to R1 plus R2 R3 over R2 plus R3. So using the voltage divider rule for that bit, sorry, the parallel product over sum rule for parallel resistance on that bit. And to do that process, you need to be able to write that out all in one go. All right? But generally, you'd calculate this, wouldn't you, in parallel, and then add it onto that one and not have any problems. But you need to. There are occasions when you need to do it all in one go. And you might need that with a voltage divider as well. Depends on the topic. Okay? So, next page is current divider. Let's have a look in your notes here. So, parallel circuits, current divider. Okay? If we have right, 2 resistors in parallel, i.e. the circuit is what I call all parallel, there's no kind of combination, okay? It's the voltage that is the same. Both of these resistors would have, if we put a voltmeter there, V1 and V2 will be the same in this case, because they're connected electrically to the same point there and there. In fact, they would all both have the supply voltage across them. So in an all parallel circuit, voltage is constant for all the components. However, the total current leaves the source. It comes to this connection, or another technical term for that is a node, where it splits. And some current goes through R1, some current goes through I2. We've got I2 flowing there, because everything that goes in comes out the other end. We've got I1 flowing there, but here those two currents add together again to become IT and all flow back to the end. So a parallel circuit divides current. Voltage is the same. We can say that the total current, because I said they add together again, it's the two currents I1 and I2 added together. That's Kirchhoff's law, which we'll formalise properly next week. Okay, and we can calculate the two individual currents, I1 and I2, using the fact that we know that the single voltage E is across both resistors. So we just do I1 as E over R1 and I2 as E over R2. Any questions about that? Well, then you've got a combination circuit, and we're coming on to them towards the end of the lesson. So we're dealing with the two separate types, series on its own, parallel on its own. Then we'll look at a circuit that's got both. All right? So, example problem. 3 resistors of 66 ohms, 33 ohms, and 56 ohms are connected in parallel to a 24 volt supply. Calculate I, the total effective resistance of the network, B, the supply current, and C, the current in each branch. So let's label those up. We've got IT there in that bit. There's I1. There's I2. And there's I3. And they would all add back together again down here to become IT again. You all understand that, yeah? So, I. How do we calculate the total resistance of that circuit? Yeah, R1 to the minus 1, plus R2 to the minus 1, plus R3 to the minus 1, and the whole lot to the power minus 1 from last week. So that equals 66 to the minus 1, plus 33 to the minus 1, plus 56 to the minus 1, all to the minus 1 equals. Push the buttons, please. 15.8 onions, tomatoes, or ohms.
Too much for the damn. You lose half, right?
At least half a mark for not putting the units. Depends where. If there's only 1 mark for that, then you lose half.
That might be right.
Might be, you know, one reason why you didn't get through. B. IT is equal to. How do we find IT now? Nice. Yeah, we could do it that way, but we don't know them yet, Lewis, do we? That could be a different way of tackling this problem. I'll talk about that in a minute.
IT equals E over R1 plus E over R2. Or you do
24
your
over 15.8.
Yeah, you can do. You just calculated RT, haven't you? Yep. Right, so that's 24 volts, wasn't it? Over 15.8 equals 1.52. Is that the 3 significant figures, Dom, or is that exact? Yeah. Okay. I mean, that's plenty, isn't it? Because from the data we've been given, the best we've got is 2 significant figures. Yeah? Alright? So now we've got the current in total. And then the question said, find I1. How do we find I1? So that's 24 over 66, isn't it, R1? Which is so 0.367 amps. You said that was 0.36 recurring.
Yeah, it's 0.3 recurring.
I'll do. I think that means that's if there's 2 dots, doesn't that mean that's 36, 36, 36, 36? Yeah. So that would be, you're right in that case, but that weren't what you said, Dom. So that would be 4. Yeah. Are we happy now? Sorry to be pedantic, but I'm correct, Dom, aren't I? Say it. Mike's correct.
Say it, Mike's correct. Tell me.
I'm only joking. A over R2, 24 over 33.
0.73.
If we're going to have them to 3 significant figures, then let's have them all. It's alright, I don't care. I'm just making a point. I3 is E over R3. All of them now, 3 significant figures. That's important, right? If you're doing, when you're doing your experimental work, you're taking voltage or current readings. If you're working to 2 or 3 significant figures, all your measurements should be quoted to that resolution. So if you're measuring 1.25 amps, 1.13 amps, and then you get exactly 1 amp, you put 1.00, confirming that that's exactly 1 to 3 figures. Alright? So, and now what you've done, obviously, Lewis, is added all them together and proved that they equal somewhere around about 1.52 amps. Yeah? Again, Kirchhoff's current law, we look at that more formally next week. Alright? So, in your notes, there are some parallel circuit questions. There's 4 of those. We'll do them till about 10 past. Alright, have a go. Okay, so the idea here is that you have to combine the analysis techniques for both current and series circuits into one circuit. So, this example on the board here, we've got E at 30 volts. Move that down a little bit. R1, 10 ohms. R2, 30 ohms. R3, 50. And R4, 15. And the question says, find all unknown voltages and currents. So we've got IT here flowing in that direction, and all those voltage arrows go against the direction of that current. So all that current flows, splits up here through R2 and R3, combines back together again here to travel back round there to the supply. Yep. Where are we going to start in trying to solve that problem? Where would you start? Find the total resistance. That's not a bad start. So, looking for the extend the page button. RT is equal to. Should we try and do this all in one go here? R1 plus R2, R3 all plus R4. Yeah. If you're more comfortable doing that bit separate and then adding the other two on, you'll still get the same answer, although you might have a bit of rounding in there with that bit in the middle. So let's put our numbers in. R1, 10 plus 30 times 50 over 80 plus 15. Plug those numbers in the calculator, we get Is that rounded in any way? No. Okay. Next. Now we know that total resistance, what can we find? We can find a total current, so we can find IT is equal to, Dom? That is 30 over 43.75 equals. So is it 6868?
That's 4.6.
That'll do. We'll have that. Near enough for me. Okay. So we know the whole circuit's 43.75 ohms, and we know the total current is 0.68, probably rounded, would it? 0.69 amps. Let's adjust that down here then. Not really, no. Well, yeah, but okay. What would we argue then? What data? How many significant figures is our data to? 2 significant figures at most. So a result like that you're going to use again later on, probably argue 3 significant figures. So we'll make that adjustment. This to 3 significant figures is 43.8. Agreed? Yeah. And then we adjust that to 43.8. Has it made a difference to the final answer for the current? $685. The key thing is the number of significant figures that are appropriate. Yeah. Normally, for the final end, you can't really quote any more significant figures than you've got in your data, but for a value that's going to be used, and we're going to use that current to calculate some others, probably best to include one more extra significant figure. Yeah. What can we find now? Now we know that that's 0.685 amps. Volt drop over each resistor. We can certainly find V1, can't we? That is I R1 0.685 times R1 is 10 ohms equals 6.85 volts. Agreed? And then we can find V4. I R4 0.685 times 15 102. Where did 102 come from? We only started with 30 volts, so we can't have 102. 10.4 then to 3 significant figures. Zero 0.685 times 15. Is it? What is the answer to this? To 3. So 10.3 to 3 significant figures. Right? Now, what 2 ways are there to determine the the voltage across the parallel pair.
So, yeah, that's quite a voltage. That's why.
Correct, that's one way. Yeah. The other way is remember, if we, from last week, if we do just that parallel combination, either through product over sum or through the 1 over R1 formula, okay, what we're doing is ending up with a single resistor that would replace those two, like that, and we were tending to call that R23, weren't we? Yeah? And you can say all of that current travels through, because all that current IT passes through that pair of resistors and come out the other side, all of that current would be travelling through that equivalent resistor. So we could do, if we'd have done this bit separately here for the combination and found R23, we could do the total current through that R23 to give us the voltage across. So we can either say V, and I'm going to call it V23 because that's the voltage across both them two resistors because they're in parallel, remember, is equal to, this is Dom's version, E minus V1 minus V4. That's equal to 30 minus 6.85 minus 10.3 equals your version, Dom.
Yeah. Oh, you want me on?
12.2 to 3 significant figures. Alright? Or we could do V23 is
I don't sound like that. No, what you want to do is yeah, sorry, I got confused with how you've done it. I did 30 minus 6.85 plus 10.3 in brackets.
Y plus.
Well, because you're adding those two voltages, aren't you?
Oh, okay. Yeah, well, that's just a different way of writing it. If you put those two in brackets like that, you've got the same thing. Yep. Exactly the same. Yep. That'll give you that bit. Yep. Yep. So what you've done then, Lewis, is you said alternative method. R23 is equal to RT minus R1 minus R4. Yeah, is that what you're saying you're done? Yeah. So that is RT was what? 43.8 on my board, minus 10 minus 15 equals 18.8 ohms. V23 is equal to I times R23. That is the I 0.685 times 18.8 equals, yeah? The point here is that there's actually 2 or 3 different ways that you could do this. Alright? So the answer to that is 12.8. That's quite a distance from that one. It depends on what you're kind of round and you've done and all that kind of thing. Personally, I would have found that value by doing just that bit. I'll put that bit in that calculation. Yeah. What do you get if you just do that? Well, I only put what people give me. What, 43.8? You've got a different, are you? Anyway, regardless of that, the method is step by step, work through the problem, find what you can find in stages to finish up with the final answer. Again, in your notes, there are some combination circuits, 3 combination circuit questions at the end for you to have a go at. Okay? So, you can have a go at those, maybe make a start now and then finish off in your own time. Again, let us know if there's any problems, and we will be going through some examples like that next week anyway when we do Kirchhoff's voltage and current laws.